Hello, stats class. Here's 8.1b. These notes will be pretty short because the warm-up was long, so we're just going to kind of summarize confidence intervals and what you should have learned from the warm-up in general. So I want you to notice that 8.1 is about the basics of confidence intervals, and then we're going to get really specific in 8.2 and 8.3 when we talk about proportions and means specifically. But today we'll get some of the statistics, or specifics, I mean. 8.1b, let's talk about what we talked about yesterday a little bit. General confidence interval is always your estimate or point estimate plus or minus your margin of error. And so our estimate is our statistic, usually x bar or p hat. We'll make it specific in a minute. Our margin of error is our critical value that many standard deviations. So our critical value tells us how many standard deviations times, they don't actually call it standard deviation in this chapter, and that's weird. It's called a standard error, and I'll briefly tell you the difference, but the difference is not super important. Well, maybe it is, I don't know. A standard deviation is calculated from the population information, which we usually don't have. If we're using a sample to estimate the standard deviation, then it's called a standard error. I'm going to write that as a sidetrack a little bit. Estimated from the sample because we don't really know the population value. So it's called a standard error or SE if it's estimated from the sample. So I want to remind you that basically what's happening here is we have our estimate, and then we go out this far, and we go out this far, and that's our margin of error. Estimate is here. Margin of error is this distance we go in each direction, and we're finding our lower bound and our upper bound for our interval. So that's what we talked about in 8.1a very generically, and we said the critical value was usually 1.96. I'm just going to say usually 1.96, which is approximately 2 standard deviations for if we're doing a 95%, which is the most common. We'll come back to that later and talk about what if it's not 95%. So that's the general idea of this unit. Specific, today we get to get specific. And you saw some of this in the warm-up when it was given to you as a formula. If you're dealing with proportions versus if you're dealing with means, you'd have specific formulas that would be based on this. What's interesting to me is on the AP formula sheet that they give it to you in this form, and they expect that you can substitute what you need. So proportions, the statistic is called p hat. And then for means, the statistic is called x bar. And then you add and subtract your margin of error, which is the critical value. Remember, we talked about this called z star, which is a special z that cuts off that 95%, times our standard error. So remember, for proportions, the standard deviation formula is square root of pq over n, except we don't know p and q. Oh gosh, that's terrible. We don't know p and q. We're going to use p hat and q hat instead. And as you might remember, q hat is 1 minus p hat. We're using the sample values because we don't know the population values. Because we don't know the population. We don't know p, which is the population proportion. If we knew p, we wouldn't need to make a confidence interval. So it's kind of ironic, really. With means, we are going to, so basically, I'm going to tell you that this is lesson 8.2. We're going to do a whole lot more with proportions. Lesson 8.3, we're going to come back to means, but I'll tell you right now what it is. It's z star again times standard deviation over square root of n. And this is, we're going to start with assuming we know the standard deviation of the population, and then later I'll tell you what it is that we're going to do with that. What if we don't know the standard deviation? We'll get to that, don't worry. So in general, our estimate plus or minus our critical value, I'm just pointing out that it matches what I said up here. So estimate plus or minus critical value times standard error. And this is our estimate plus or minus our critical value times standard error. You're going to end up memorizing this because we're going to use it so much. At least you're going to memorize this concept. So anyway, we're doing, in fact, that's so important, I think I'm going to write it again because it leads into the next thing I want to say. Both of these are the estimate plus or minus the critical value times the standard error. And so in this homework, they're going to start making you calculate these with actual numbers, and that's nice. You'll use 1.96 unless they tell you otherwise. But I want to talk specifically today, more than the calculations, I want to talk about why these three things work. Because this kind of fascinated me when I first learned this, that these three pieces actually come from what we learned way back in chapter 1, which was the center, shape, and spread. This estimate, this spot right here, is the center of your confidence interval, and we want it to be unbiased. We want it to be approximately the same as the thing we're trying to estimate, which is our parameter. That center is the estimate. We'll come back to that in a second. The critical value is a z-star, which is calculated from the 95% thing, and we talked about how we do that on the normal curve in the 8.1a notes, so I'm not going to make you write this again, but here's a reminder of what we did in 8.1a. We talked about the normal curve and calculating where that z-star would be based on inverse norm to get it to cut off the middle 95%. That's based on shape. We can't do that calculation unless the shape is approximately normal. So that's based on shape. And then standard error, also called standard deviation, but this is estimated, okay, whatever. Regardless, standard error is a measure of spread. Isn't that kind of fascinating that shape, center, and spread are coming back again? And that could help you remember the three pieces of this formula. In fact, these three pieces only work under certain conditions, which the good news is you've seen them before. The center will be unbiased if you have a random sample. So if you have a random sample, that means you end up with an unbiased estimator, and that means you have the correct center for your interval. So that's how you accomplish that unbiased center. So this piece works if you have a random sample. This piece works if you have the right shape, and the shape we want is for it to be approximately normal, so that that z-star calculation is correct. How do you know if it's approximately normal? Well, that's based on some of the stuff we learned in chapter 7. If p hat, the sampling distribution of all the p hats, is approximately normal, if np and nq are both greater than or equal to 10, that's if we're dealing with proportions. If we're dealing with means, we need to check that 30 rule, if the sample size is greater than or equal to 30 for means. So we have rules we can use that we've seen before in chapter 7 based on what we learned about sampling distributions. If whichever one of these is appropriate is true, then the shape is normal, and then this critical value calculation is accurate, and that's what guarantees that 95% thing that we were talking about. And then the third one is spread, which is the standard deviation formula, and this is like way back to chapter 6. Those standard deviation formulas only work if the variables are independent, or if the samples are independent of each other. So independent is the key to this. The way you check to see if it's independent is that 10% rule, which is the sample size has to be less than or equal to 10% of the population size, which is n. Sample size, population size. And that allows us to ignore the problem of sampling without replacement. We will come back to this again and again all through the chapter until you have these three conditions memorized, which is going to just come naturally. You'll see them so often. That's how you memorize things. Sampling, oops, I left out the word without replacement. So we can ignore that problem, because if you sample without replacement, then every time you take a new sample, it changes the probabilities of everybody else. And so we can ignore that if we have a large enough population that's more than 10 times our sample. And that's what makes this formula accurate, basically, or this formula. So all three of these formulas are based on good statistical data gathering practices, right? You want to be sure that you have a random sample. You want to be sure your sample is large enough so that you can use the normal distribution calculations. And you want to be sure that you have your sample or your population large enough so that your sample is small enough. Like, your sample has to be large enough and small enough at the same time. That's kind of annoying, isn't it? But if you do that, if you make sure that these are true, all three of these things are true, then this formula accurately gives you a 95% confidence that you are right, which is where we're headed in this chapter. So I told you these notes would be short. That is all I have for you today. We will do long notes on Thursday to make up for that. But that is the end of lesson 8.1.